Okay, so yesterday we finished the subject of oblique shock waves. We have seen different, let's say, aspects of oblique shock waves, different situations regarding shock reflections and interactions, and then we started another physical phenomena that we encounter when we are dealing with supersonic flow, and this phenomena is basically when a supersonic flow has to uh, instead of going through a compression like it does when it's let's say it gets subjected to a geometrical change and it gets subjected to some kind of compression, instead of where we have normal or oblique shock waves, it has to go through a geometrical, let's say, disturbance such that the gas needs sudden expansion. Okay, and then that physical process, for example, can occur through this like a corner, like this corner here, and then that physical process, when it's occurring through this corner, it basically the flow instantaneously has to adjust itself fundamentally to an increasing area, and that needs to, and as we discussed yesterday, but we will discuss more in coming weeks regarding that. But in any case, it has to go through this sudden expansion, and this expansion has to generally in the physics of supersonic or compressible flows or supersonic compressible flows happens through a series of Mach waves that are uh, emanating from the corner where we generate the geometry change. And these series of Mach waves are called expansion waves or expansion fan. And specifically, we call them Prandtl-Meyer expansion fan. And similar to what we did for the shock wave analysis, what we would like to know are, like here, given the inlet conditions, Mach number, and other flow parameters, when this supersonic flow goes through this expansion fan, how can we find actually the parameter values downstream of this expansion fan? The new Mach number and the pressures, densities, temperatures, etc. So this expansion fan process, since it's composed of basically many numbers of Mach waves, and we did discuss Mach waves a few weeks ago, and it's a Mach wave is basically an isentropic process. So there's no entropy generation, a single Mach wave. We have many of them here. So this expansion process is basically an isentropic process. Now, the thing is, what are the relevant equations and to analyze this problem? So, by the way, where can this happen on a real geometry? For example, like where can we have like a gas expansion? Where could this happen on a real geometry? Well, for example, on a geometry like that. Okay, so this is maybe some kind of missile, and then it's flying supersonically. It would have, under design conditions, attached, let's say, oblique shock waves here. And then, for example, if the flow may be outside the missile, it could be still supersonic. So it's supersonic here. It could be still supersonic here. And then, for example, right at this corner, it goes through a sudden geometry change. So at this corner, one could expect expansion fans, okay, for example. So in this very simple geometry, of course, if it's for example, supersonic flying fighter aircraft configuration, then manned or unmanned, whatever, it doesn't matter. Then, depending on the local geometry changes that is happening, if there is some supersonic flow happening over those geometries, you could end up with expansion waves at certain points. So we need to understand the physics, plus we need to come up with some equations that we can use to calculate gas properties.
Hocam,
Yes.
in shockwaves, we have such phenomena that if our theta angle or geometric angle is higher than a certain value, we have detached shockwaves. Do
Mhm.
we have same phenomena in this expansion waves?
No, we do not. We do not have, because physically this is a different process. We will discuss this, okay? It's a different process. This is not a compression process. This is an expansion process. So physically it's different, and we do not have such a thing. The short answer is like that. Okay.
Teşekkür hocam.
So we will, since the expansion fan is composed of a series of Mach waves, we will concentrate ourselves only to a single Mach wave first, sitting at an angle to an incoming, let's say, flow field. So some velocity is incoming. Here, the Mach wave is sitting at an angle, and some Mach angle. And then, due to the effect of this Mach wave, the flow experiences a slight direction change. So, of course, I will exaggerate it here. The vector will change direction, plus its magnitude could slightly change after the Mach wave. So, uh, so basically, if we basically let me continue like that. If we basically work out this case geometrically, okay, work out this case geometrically like that, and here this angle is again going to be the Mach wave angle. This angle is 90 degrees, and this angle, we call it, it's a small deflection from the original, so let's call it dv. I'm sorry, not dv, d theta, not the velocity but the angle, slight deviation. So therefore, for example, this angle is therefore pi over 2 minus mu plus d theta, and this angle is actually a pi over 2 plus mu from the geometry in this triangle. So using this, we can actually, and by the way, this component will be equal to the original velocity here. So this is, I mean, the triangle is such that this is also equal to V. So we construct this triangle like that. So under this case, from this geometrical layout, what we are interested in is, for example, some kind of relation relating the velocity level after the Mach wave to the velocity level before the Mach wave. And from these velocity vectors here, this is v plus dv here, and this is basically v here. These are related, obviously, to the trigonometric relations. For example, one can write that v plus dv over v is equal to sine pi over 2 plus mu, and sine divided by sine pi over 2 minus mu plus d theta, but mu minus mu minus d theta. We could write this. In our derivation process, we will call this equation 1. This is from the geometrical layout that we've just drawn here. So the question is, what are these angles? What are these sine functions and everything? For example, sine pi over 2 plus mu, which shows up in the numerator of that equation, equation 1, this is actually, one can write that this is actually equal to cosine mu. So we call this equation 2. And similarly, the bottom part of the ratio denominator is equal to pi over 2 minus mu minus d theta. But one can actually open up this trigonometric equation. We could write this is equal to sine pi over 2 multiplied by cosine mu plus d theta. And so minus cosine pi over 2 and multiplied by sine mu plus d theta. Okay, and sine pi over 2 is, for example, 1, cosine pi over 2 is 0. So that's why we end up with this equation. This becomes equal to cosine mu plus d theta in reality. And we open up this one. We don't stop there. This is equal to cosine mu cosine d theta minus sine mu sine d theta. So let's call it equation 3. So basically, we substitute 2 and 3 into equation 1. So 2 goes here, 3 goes way up above here to equation 1. And then we end up with a modified relation for v plus dv over v, which I can write 1 plus dv over v becomes equal to cosine mu, this is the Mach wave angle, and divided by cosine mu cosine d theta, that's the deflection angle, infinitesimal deflection angle that is created by the Mach wave, and minus sine mu sine d theta. Okay. So we know that a Mach wave creates an infinitesimal change. So d theta angle is a very small angle. So we can further do some simplifications. D theta is a small number, a small angle. So that, for example, cosine d theta is approximately equal to 1. So maybe it's equal to 0.9999, but it's approximately equal to 1 for small angles. Similarly, sine d theta will be approximately equal to d theta itself because in radians, again, because of the small angle condition. So that simplifies our relation even further, which reads as 1 plus dv over v now is equal to cosine mu divided by cosine mu minus d theta sine mu. Okay, and in fact, one can write this as, if I take this cosine mu to the bottom of this equation, to the denominator, I can write 1 over 1 minus tangent mu multiplied by d theta. So now it is a quite simplified equation. So I have an equation for this infinitesimal change in velocity as a simplified equation written in terms of the Mach wave angle and this deviation angle d theta. We'll keep going. So if I just call this tangent mu d theta as x, so it looks like an equation like 1 over 1 minus x. So in reality, in mathematics, this equation can be replaced by a polynomial approximation, infinite series. So this can be equal to, written as equal to 1 plus x squared plus x cubed. It goes like that for x values smaller than 1. So for positive values of this infinite series approximation can be done. So using this mathematical, let's say, identity, we can write then 1 plus dv over v becomes equal to 1 plus x, so our x is tangent mu times d theta. and plus, well, higher order terms. Okay, they're squares, they're cubes, higher order terms, which could in fact be neglected practically, because magnitude wise they will be quite small compared to these higher order terms, will be quite small when they take their squares and cubes. They will be quite small compared to 1 and compared to the second term, so they can be ignored. Higher order terms ignored, let's say. So basically then what we can write is 1 cancels this one. We got a relation for d theta, which is equal to dv over v divided by tangent mu. Let's call this equation 4. So we have a nice compact equation which relates, slight angle change that is happening through the Mach wave. What kind this slight angle change causing basically the velocity change, or in order to have this velocity change, you need to have this much of angle change. You can explain it in either way. We know actually one more fact regarding this angle mu, the Mach wave angle. We have seen that previously that this is equal to arc sine 1 over Mach number. So whatever Mach number is in front of the or upstream of the Mach wave, that can be used to calculate the Mach wave angle actually. So we can make use of this. So if this is the case, from here, in fact, I mean, this basically means that it basically represents more or less a triangle like this. So this is, let's say, 1, this is m, and this is mu. So sine mu is equal to 1 over m. But in that case, this edge becomes square root m square minus 1. Why am I doing this? Because I can get tangent mu from here, from this triangle, and tangent mu appears in this equation. So that's what I want, why I want to do this. So therefore, substituting this now identity into equation 4 instead of tangent mu. So we can write, okay, let's use this in 4, and we end up with d theta now is equal to square root m square minus 1 dv over v. Okay, so this is equation 5. Now, on the right hand side of this equation, now I don't even see any angles or whatever. I just see a Mach number, which is basically the Mach number of the supersonic stream approaching just upstream of the Mach wave. And this is the delta velocity change occurring through the Mach wave, which is relating to the delta angle deviation of the velocity vector. So what else? We know that, okay, the question is then, what is dv over v, for example? Can I replace this also with some kind of Mach number? Well, I must be able to, because velocity is related to Mach number. So we should be able to do that. In reality, velocity is equal to Mach number times speed of sound. We know that. So from here, in fact, if we take first the natural logarithm and take the derivative, one can show that dv over v is actually, it can be written as dm over m plus dA over A. This can be driven starting from this relation mathematically. We take the ln, we take the derivative of ln of both sides of this equation. So first we take ln v is equal to ln ma, then we take the derivative d of both sides. So this can be derived actually from that. Because ln m times a is ln m plus ln a. So you see where that's going. So that's equation 6. We will make use of that. And what about A? What about A here? I mean, if I would like to replace dv over v with this equation, it's fine. I have dm over m. I have the Mach number. But what is A now? Can I actually get rid of speed of sound here and write it somehow in terms of Mach number as well? One equation that I can use for that is the isentropic relation. For example, I know that, let me first write this. For example, the relation, the equation relating the stagnation temperature to static temperature is equal to 1 plus gamma minus 1 over 2 m square. I know that. But there's also one thing more that I need to know. This is also equal to the ratio of a0 square over a square. So the only thing that you need to do is to multiply with gamma times r, both sides here, so it becomes a0 square, multiply with gamma r, divide by gamma r, so a0 square over a squared. It's the same equation from here. So we got a relation relating a to a0, which is basically 1 over 2 gamma minus 1 over 2 m, I'm sorry, 1 plus gamma minus 1 over 2 m square to the power minus 1 over 2. So again, I need the a over a. So basically what we do is we take the natural logarithm of both sides. ln of a is equal to ln of a0 times this. And then take the derivative of that as we did before. So we can obtain a relation. Let me first put a note here. Take ln of both sides, and then take derivative. Let's keep this as a note here. And doing that, I can obtain an expression for dA over A, which I can use here, in equation 6. And this dA over A will be just a function of Mach number and nothing else. This will be equal to minus gamma minus 1 over 2 times Mach number multiplied by 1 plus gamma minus 1 over 2 Mach square dm. Okay, so we reached equation 7. Now we have an expression for dA over A, which is entirely written in terms of Mach number. So dA over A is a function of Mach number. I have dm over m here, which is equal, so the summation is equal to dv over v. So entire right-hand side of equation 5, d theta will be equal to just a function of Mach number and nothing else. So that is quite useful now. So substituting this into, first of all, substituting equation 7 to equation 6, first of all. So substitute 7 into 6. We get an expression for dv over v, first of all. It looks like that. 1 over 1 plus gamma minus 1 over 2 Mach square dm over m. So that's the relation that we need for d theta on the right-hand side of the equation for d theta. Let's call this equation 8. And now we substitute this one into d theta equation. And then let me see, where was our d theta equation? D theta equation is here. It's just square root of m square minus 1 times dv over v. But now we do have an expression for dv over v. So d theta, therefore, will be equal to square root of m square minus 1 divided by 1 plus gamma minus 1 over 2 m square dm over m. Now, the thing is, this is for this is a differential equation, d theta on the left-hand side, dm on the right-hand side, and the function before dm is entirely written in Mach number. So, for example, if I would like to integrate this one, the left-hand side and right-hand side of these equations, I can integrate, for example, d theta will be the, or I can, let me put it this way, let me put it up. So I can integrate, for example, the left-hand side and the right-hand side. So when I integrate d theta, I will get an angle theta. And that angle theta can be calculated by integrating this from an upstream Mach number to a downstream Mach number now, m1 to m2. And it involves integration of this equation, square root of m squared minus 1 divided by 1 plus gamma minus 1 over 2 m squared dm over m. Equation 9. Now here, this equation tells me this. I mean, if there is some sort of incoming supersonic Mach number, and it has to go through a direction change, and it will through some kind of expansion to a level m2, the angle, this angle change can be calculated as a function of m1 and m2. Okay, so either somebody gives you m1 and m2, you can calculate theta, or if you, after the integration of this equation, somebody gives you m1 and theta, you can try to estimate m2. So you see how this is going to be useful in our expansion fan calculation. Now the thing is, this function here, including, I mean, this actually the entire right-hand side here, is known in compressible aerodynamics, is represented by the Greek letter nu. It's called the Prandtl-Meyer function, nu m, and its definition is this. So I will rewrite it again. It's the integral of square root of m squared minus 1 divided by 1 plus gamma minus 1 over 2 m squared dm over m. And this is known as the Prandtl-Meyer function. Okay, Prandtl-Meyer function. Well, what is this function? I mean, of course, it involves it involves the integration of this quantity with respect to Mach number. Not very straightforward process, but I guess with today's technology, you can go to MathCAD or whatever, or Wolfram website, you can symbolically integrate this anyway. But when you integrate it, this function turns out to be nu m is equal to square root of gamma plus 1 over gamma minus 1 multiplied by a tangent, arctangent of square root gamma minus 1 over gamma plus 1 m squared minus 1 minus arctangent square root of m squared minus 1. So this is what you get after the integration, the actual equation for the Prandtl-Meyer function. So how do we actually make use of it? Let's say when we would like to calculate this integral up here, the theta integral, this one. This theta integral is a definite integral. It involves integration of the Prandtl-Meyer function from m1 to m2. Okay, so it's basically the evaluation of this new function, the Prandtl-Meyer function at m2 minus its value at m1. As simple as that. So the definite integral in so the equation for theta, I can say equation for theta can be written as this. So theta will be simply equal to this Prandtl-Meyer function evaluated at M2 minus the Prandtl-Meyer function evaluated at Mach 1. The Mach 1 meaning upstream of the, for example, Mach wave, and downstream of the Mach wave, or if you have many Mach waves, so you can consider it as the total turning angle. Here, nu m is given by this equation 10, and this is for a calorically perfect gas. Because assuming gamma is equal to 1.4 and all that, for a calorically perfect gas, this is true. So how do we actually make use of this when we are dealing with expansion, Prandtl-Meyer expansion problems in supersonic flow? There's a procedure. I will write down the procedure step by step. It consists of 4 steps. So using this Prandtl-Meyer function. So expansion fan calculation procedure, we can say. Calculation procedure. So the first step is, of course, our starting point is the upstream conditions, meaning that the M1, for example, the upstream one Mach number should be given. So for given M1, we obtain new value for that, new M1. Now, new M1, obtaining new M1 means just simply plugging M1 into this equation, calculating the new value. By the way, what is the unit of this? What is the unit of the new value? Any ideas?
Radians.
Radians, right? It has to be consistent with this because it is related to the angle, so it has to be in radians. So we will calculate in the first step for a given M1, you plug the values in and you get the new value. This is one option, but generally this equation is already, the integrated values for certain different Mach numbers are already listed in your book as well. And generally in compressible aerodynamics books or in aerodynamics books, these integrated values are listed for a given, let's say, M1 value. You can just look at the appendix in your book. If I'm not mistaken, it must be appendix C, I guess. So you can find this value, new M1. So either from equation or from tables, let's say, listed tables. So we got that, and then we need to calculate new M2. Okay, now we calculate new M2 from equation 11 here, from equation 11 using known or given, let's say, theta value. Because if you remember our original problem, is that we have a certain geometry like that, and the supersonic flow goes through this expansion fan because of this sudden sudden direction change, and this direction change occurs here with an angle theta. So this theta value, the rotation value, will be calculated in order to obtain the new M2 value. How? In radians, but basically what we need to do is we just obtain new M1. We take it to the left-hand side of this equation. We know the radian value for theta. We add them up, and then we get the radian value for new M2. For new M2 in step 2. So new M2 from equation 1 given theta value. Okay. Next step, the third step, is that now that we know the new M2 value, we go back to the table. So again, we do kind of a reverse calculation now. left-hand side of this equation as new M2, but we would like to calculate the M2 value here, this Mach number value here listed in this equation. Of course, doing this through this equation is basically not that straightforward. Doing that, I mean, giving the left-hand side and trying to come up with the Mach value that satisfies the equation is not straightforward from the equation. So basically what we do is we use tables again to do that. So basically we obtain M2 value again from tables. Okay, how? Because in those tables we have basically two columns. So M column, different Mach numbers are listed here, and new M values are listed here. So in this third step, we have the value for new M, and then from this table we will find the value on the left column that will correspond to that new M2 value. It could be in those tables, it could be sitting between two Mach numbers. For example, if these are listed, just as an example, if these are listed as, for example, Mach 2.1, 2.2, 2.3, it goes like this, and then somehow you obtain your new M2 value, and you may need to interpolate between these Mach numbers. Okay, so this will have a new at 2.1. You will have a new value at 2.2, you will have a new value at 2.3, but if the new value that you calculated at step 2 here is somewhere in between these, for example, you will have to interpolate the Mach number accordingly. Therefore, we obtain an M2 value from tables, and corresponding to the value of new M2, let's say using the value of new M2 from step 2. Okay, so once we do that, now we do have we do know the Mach number. These are the expansion fan lines, Mach wave lines. When we reach step 4, now we do know Mach 2. So and we do know Mach 1, this is calculated. We do know Mach 2, this is calculated. And the nice thing is the entire expansion fan process is isentropic. So expansion fan is a isentropic process. So basically we can use all isentropic relations, to calculate the required flow properties. Isentropic relations like what, for example, if we are interested in, I don't know, the temp, for example, if the free stream static pressure is given, let's say P1 is given, using the isentropic relation P01 divided by P1, which is equal to 1 plus gamma minus 1 over 2 and 1 squared to the power gamma over gamma minus 1. If P1 is given, I can calculate P01 here. But since this is an isentropic process, the expansion fan is an isentropic process, this is going to be equal to P01 will be equal to P02 due to the fact that this is an isentropic process. And from here, I can use the same isentropic relation then, which relates P02 to P2, okay? And this is written as a function of M2 after downstream of the expansion fan, gamma over gamma minus 1. So from here, M2 is known, P02 is known, P2 can be calculated. So one example, okay? Regarding temperature, if T1 is given, you can do basically a similar thing, but anyway, just to be complete quickly, let me write this down. T0 1 over T1, 1 plus gamma minus 1 over 2, and 1 square, and 1 is given, T1 is given here, it's the upstream condition, so I can calculate T01. T01 is calculated, but isentropic and isentropic process, so it's also adiabatic, so T0 also does not change. Well, it does not change even in shock waves. In expansion waves, it does not change either. T01 will be equal to T02, so I can get, again, use the same relation now, T02 over T2 equal to 1 plus gamma minus 1 over to M2 square. M2 is known, T02 is known. Here I get T2. Okay, so now I have the stagnation temperature, pressure, static pressure, temperature after the expansion fan, and also, of course, using equation of state, I can also calculate ρ2 density. Okay, so basically, just since it is an isentropic, see, we couldn't do this for shock waves because this is kind of a similar procedure to shock waves because it starts with finding out the Mach number at 2. This is also how we started in the shock wave calculation. However, the problem is in a shock wave, the process is not isentropic, so we cannot do all of this stuff. Okay, we needed to derive special shock jump conditions for pressure jump, temperature jump, and density jump. We couldn't do this. But now, again, here in the expansion fan, we start with the known Mach number condition upstream and downstream. But unlike shock waves, this is an isentropic process, so we could very easily relate the conditions like that to each other and make use of the isentropic relations as we have just used here, and calculate the properties after the expansion fan. Now, so basically, in order to solve such a problem, I mean, normally in the first few steps, let me first go here, revise the steps. For given M1, calculation of new M1 is not a big deal. I mean, you can, of course, use the equation or use the tables. But the second step, second step is from theta. The third step is not straightforward. You cannot use the equation to calculate third step unless you have some, some symbolic solver or whatever, or you need to write a code, iteratively solve it or whatever. You cannot just right away do it. So instead of doing those, we have to work out the tables. So that's important. So which means that for solving expansion fan problems, we do really need to have these Prandtl-Meyer function tables listed in order to obtain a solution. One application before we finish today is, for example, the flow around like a diamond shape, the supersonic flow around a diamond shape. Okay, so let's say we have this kind of a diamond looking shape, and let's say this is the axis, and this is subject to 0 angle of attack supersonic Mach number. Okay, in this kind of problem, I mean, the angle of attack doesn't have to be 0, but just for simplification purposes, I'm going to describe it like that. But if it's different than 0, we discussed it quite a bit yesterday, if you remember. Anyway, if it's 0, this kind of geometry will generate, first of all, 2 oblique shock waves in the front. So there will be some kind of again, supersonic Mach number after the 2 oblique shock waves. And then at this corner, the flow, the geometry deviation is away from the flow, as you can see here. It's like that. It's away from the velocity vector. So we will end up with an expansion fan at this corner. Similarly, we will end up with an expansion fan at this corner. Then when we come what we can say as the trailing edge point, the flow again will turn towards itself, and we will end up with another set of oblique shock waves, but the angle of these could be different than the front ones. Okay, so as the flow streamlines are going and trying to follow the geometry like that, they will have to go through first, for example, on the top side, first an oblique shock wave, and then through an expansion fan, and then through another oblique shock wave until they reach the downstream condition of this diamond shape. So, for example, similar to the example that we did yesterday, by finding Mach numbers, let's say in this region, and in this region, if the angle of attack is 0, it will be symmetrical. So if you find the Mach numbers in this region, and therefore all the flow properties in this region, static pressures, for example, which means that you can also calculate static pressure distributions on these surfaces, which you can use to calculate, for example, the drag acting on this diamond-shaped body. If the angle of attack is different than 0, so M1 is coming like that with an angle, it will also create lift because the chord line, there's an angle to the chord line. Angle of attack is not 0, so it will also generate lift force in addition to the drag force, which can also be calculated using the local pressure distributions on the surface. And of course, when there is an angle of attack, the shock wave configurations will not be symmetrical. You have to take that into account. Yesterday, I think, yesterday, somebody, or was it last week, somebody asked me whether there's going to be a recitation hour. We talked with Mustafa Hoca. I think there will be, normally, we were not planning to do a recitation hour, but we will also, I talked to one of the course assistants, and I talked also Mustafa Hoca. I think there will be a recitation hour, and examples like these will be solved, few sample problems regarding these kind of applications, which include both implementation of shock waves and expansion fans in around one geometry. Sample problems related to these kinds of problems will be solved during the recitation hour. It will be announced, I think, soon in the coming days. Okay. Anyway, so it's 2:30 right now, so let's stop here, and we will continue actually with a new topic next week, again under the context of supersonic flows, but with a different topic. Okay, so any questions?
Hocam, is there a possibility to get 2 or more possible Mach number for an arbitrary Prandtl-Meyer number in the reverse step?
In the reverse step, I think not. Let me see. I think not. I think we only get one Mach number. There's only one single solution, if I remember correctly.
Thanks.
I will check that, but it's a good point.
Thanks, sir.
Any other question? Okay, then let's stop here.
Hocam, can I ask something about that diamond shape?
Yes, of course. Do you want me to share it? Okay, I shared it. Yes.
After M2, we have M3. In that angle change, do we take theta like yesterday with angle of attack, or no?
No, if the angle in this case, I mean, the important thing is the direction change of this vector when from M2 to M3.
It's like yesterday then.
Yeah, so this is the important angle when you're calculating the expansion fan here.
Okay, thank you hocam.
If there, I mean, this angle can be calculated obviously, but if there is an angle of attack, it may affect that. You have to be careful. But the important thing is the direction change of this vector to this vector. So as you said, it's like yesterday that we discussed it. Okay.
Okay hocam. Thank you.
Good. Any other questions? Okay, guys, so let's stop here and let's continue next week on, when was it? Wednesday. Yeah? Let me stop recording.
İyi günler hocam.